subscriber in my channel is outside India. I need more support from India also. Please share my video as much as you can. It will be great motivation for me. I am getting approximate 10 emails plus telephone call in one day. I am trying very hard to reply everyone within a day. More of the videos are in pipeline. Please your love and support continue with me. I would provide you more videos in future. Thanks to all for supporting to me. Let's start. Today's topic is design and analysis of electrostatic charged plasma based dopingless IGZO vertical nanowire FET for ammonium gas sensing. Simply we are designing a nanowire FET gas sensor. There are different problems with the conventional FET, or we can say that nanowire FET. First one is the abrupt junction is required in FET. Require costly doping techniques such as diffusion and ion implantation. Third one, random dopant fluctuation. Fourth one, high temperature annealing required. And the fifth one is a high thermal buzzer. During diffusion and ion implantation, some atoms are dislocated from the position. This condition is called random dopant fluctuation. So that a high temperature process is required to move the atom into the original position. So that the thermal buzzer of the device is very high. These are the drawbacks of the doped FET. The solution of the above mentioned problems is charged plasma FET. In the charged plasma TFET, no abrupt junction is required. Second one, no high thermal annealing process is required. No random dopant fluctuation. So that due to the no random dopant fluctuation, thermal buzzer of the device is very low, is very less. Less mobility degradation. Charged plasma FET solve the problem of VT variability also. In charged plasma FET, there is a no doping, so that no costly doping technique, diffusion and ion implantation is required in charged plasma FET. There are two methods of inducing charge carrier in the intrinsic body. First one is the electrostatic technique and the second one is the charged plasma technique. The electrostatic doping technique show excellent unipolar characteristics. Electrostatic doping introduced with the help of polarity gate at the source and the drain side. In the electrostatic technique, appropriate bias is connected at the polarity gate for inducing the desired number of carrier in the desired level. This process is referred as electrostatic doping. The electrostatic doping disposes of necessity of external doping. Thereby, it will yield low thermal buzzer and it will also simplify the fabrication process. The major concern of the electrostatic technique is power consumption. The power consumption of the device is high due to the use of extra biasing at the source drain side. The second technique is charged plasma technique for FET. In charged plasma concept, without the need of any doping, the P plus and N plus are induced in the intrinsic silicon body by choosing appropriate metal electrode with suitable work function. High work function will induce holes and the lower work function will induce electrons in the intrinsic silicon body. Absence of high doping concentration gradient leads to simplification of fabrication process of charged plasma FET, field effect transistor. Work function of a source drain metal electrode should be greater than or less than psi electron affinity plus Eg by 2q respectively. For making P plus metal work function, 5.93 work function is required. 5.93 work function is of platinum metal electrode. For making N plus metal work function is 3.9 electron volt is required. Hafnium has a 3.9 electron volt work function. In the proposed structure, I am using IGZO material for sensing the ammonia gas in nanowire FET device. IGZO, indium gallium zinc oxide, is an artificial semiconducting material consisting of indium, gallium, zinc and oxygen. The proposed device is designed with artificial material IGZO because of its transparency and temperature stability. IGZO has a high mobility material which is used as a body material. The most significant advantage of using IGZO is due to its transparency at visible wavelengths, which have shown to possess surprisingly high electron mobility compared to more traditional amorphous semiconductors such as silicon and organic semiconductors. IGZO material prevent mobility degradation due to external photon absorption. Electrostatic charge plasma technique is used to design dopingless vertical nanowire field effect transistor to form source drain region on the intrinsic silicon body. Electrostatic charge plasma technique is used to form a source drain region on an intrinsic body of IGZO material. At the source side, the N plus region is formed by selecting the appropriate work function of the metal electrode, and at the drain side, the N plus region is formed by giving biasing to the metal electrode. The electrostatic technique is used at the drain side. The metal deposited over the oxide layer is used for drain side polarity gate with applied VDS. Therefore, the fabrication process becomes simpler as compared to the individual dopingless technique. Charge plasma technique is used on the source side where appropriate work function metal is used for source metal to develop n-type doping in the source. Therefore, no requirement of the extra biasing at the source side is needed and overall power consumption is reduced. N plus channel dopingless vertical nanowire FET with the catalytic metal gate is proposed for ammonia gain sensing. Cobalt, molybdenum, and the lutetium are used as a gate electrode in ammonia gas detection due to their high reactivity towards ammonia. Also, we have compared their on and off current of the proposed device toward the gate adsorption. Due to the presence of gains on the gate, the metal work function of the gate changes, which varies the I off current and the I on current of the proposed device, and it also changes the threshold voltage of the device, so that these three parameters I off current, I on current, and the threshold voltage are considered as the sensitivity parameter for sensing the ammonia gas molecule. Advantages of ammonia gas detection. Ammonia detection has gotten impressive consideration in the field of agriculture, environmental monitoring, chemical and pharmaceutical processing, and disease diagnosis. Nowadays, MOSFET-based gas sensor and chemical sensor are mostly used because of their low cost. Due to the large volume to surface ratio, this sensor shows the better sensitivity and fast response time at room temperature with the lowest power consumption. Vertical nanowire with catalytic metal gate film is designed for ammonia gas detection. Cobalt, molybdenum, and ruthenium are used as a catalytic metal for high sensitivity. The sensitivity of the proposed device has a critical role in the designing of ammonia gas sensor. This can be done by using the simulation tool SILVACO ATLAS TCAD tool. For designing electrostatic charge plasma based dopingless IGZO vertical nanowire field effect transistor, the simulation was performed through SILVACO ATLAS tool, considering as three-dimensional system framework. 3D cubic geometry is defined for designing of IGZO vertical nanowire field effect transistor. It is a point to be noted that 3D cubic geometry is used, in which I have introduced z-axis with x and y meshing, so that the device is in three-dimensional structure. The length and thickness of the channel are taken as 20 nanometer and 10 nanometer respectively. Drain and the source length is 20 nanometer respectively. HFO2 is used as a oxide layer, and the thickness of the oxide layer is 1.1 nanometer. To implement electrostatic charge plasma technique, nanowire source, drain and gate are kept intrinsic. Electrostatic technique is used at a drain side so that nickel silicon metal is used for drain side metal and the BDS is applied at it. Charge plasma technique is used for source side, so lower work function 3.9 electron volt of hafnium matter is used at the source side to develop N plus type doping in the source side. The drain metal is polysilicon with default work function is 4.17 electron volt. Polarity gate length is 10 nanometer at both sides and spacer thickness is 10 nanometer. For designing of ammonia gas sensor with high sensitivity in IZO vertical nanowire field effect transistor, catalytic metal as a gate metal is proposed of 1 nanometer thickness. Cobalt, molybdenum, and the ruthenium are good catalytic reactive metal for ammonia gas sensor. Drain to source voltage are VDS and the gate to source voltage are VGS, and its value is 1 volt and 1.5 volt respectively. The parameter used for the simulation are channel length 20 nanometer. I have already told you about that. Channel thickness 10 nanometer, spacer thickness 10 nanometer, gate oxide thickness 1.1 nanometer, doping uniform doping, intrinsic doping, drain voltage 1 volt, work function of gate 4.8 electron volt, work function of drain 4.17 electron volt, work function of source is 3.9 electron volt. Let's go to the code. Start from the same statement, go atlas. The mesh 3.d X meshing start from the 4.9 nanometer up to 19.1 nanometer. Y meshing is start from the 4 nanometer up to 68 nanometer. With the different location, with the different spacing, you can note down this code and run on your computer. If you want to define your result, you can change the meshing to as close as possible. Please note down carefully. Next is the Z meshing. For making 3D structure, I have introduced Z meshing. Z meshing is same start from the 4.99 nanometer and up to 19.1 nanometer with same spacing 3.8 nanometer. Next, I have defined the material and the reason. I have defined total 13 reason. Starting from the first reason is the IGZO material with their positional parameter. Second up to 13. All the reason the material is same, that is hafnium oxide material with their positional parameter. Please note down very carefully. Hello my dear friends, this is my earlier code. You can also combine 2-3 hafnium oxide resin and make one resin. Please note down. Next in the code is the electrode. First electrode is for drain, second and third for the source, and the fourth, fifth and sixth electrode is for the gate with their positional parameter. Second source electrode is used for the gold material. That is good for when you are designing the GaN sensor. We are applying electrostatic technique at the drain side, so that we have to require more electrode terminal at the drain side. This is 4 drain electrode I am using in my proposed structure. I have already told you about that. This is my earlier code. You can also combine 2 or 3 electrodes to make one electrode. If you want to run the program as it is, please note down all the positional parameter very carefully. If you are making a mistake, you will get the runtime error. Most of the students are calling me and said that we are not getting the result. If you are not note down properly, you will definitely get an error message. Please note down all the resin material, electrode material with their positional parameter very carefully to obtain the same result. Next is the doping concentration. You can also take one resin with uniform concentration, that is intrinsic concentration, at the source, channel and drain region. In this code, I have taken same doping in the different region. Next, I am defining the contact. Gate work function is 5 electron volt. You can next contact name drain. At drain side, we are applying electrostatic technique. This means we are inducing the charge carrier with the help of the biasing voltage VDS. At the source side, we are applying the charge plasma technique. In the charge plasma technique, we are applying a propel matter work function to induce charge carrier at the source terminal. Next is the model field mobility, SRH, concentration mobility, BQP model. In the last video, I have already explained about this model, BQP model in detail and their value N gamma and N alpha at room temperature. Next is the output electric field. This code is used for getting the balance band, conduction band, electric field and potential etc. from the structure file. Next, I am using the method statement Newton and Arnold. We are running this code for two different VDS voltage. First voltage is 50 millivolt and the second voltage is 1 volt. I am using the loop statement to run the program at two different VDS voltage two times. I have assigned VDS voltage as Vn at two different voltage 1 volt and 50 millivolt. Solve initial statement. Then we are run the program. Solve initial statement. After that, solve name drain, V drain, start from 0 up to the Vn voltage. When first time the loop is run for the 1 volt and the second time it's run for the 50 millivolt and the voltage stepping is 25 millivolt. Save the structure file. Next, save the log file. You can observe these two files with the help of Tony plot statement after the loop end, in which I am using the Tony plot overlay statement. This means we are plotting two different curves in one graph. Next, I want to extract some parameter from the log file 50 millivolt as well as 1 volt. First is the subthreshold slope. This is the formula for the subthreshold slope. If you are using in the code, you will get the exact value of the subthreshold slope. Second one is the off current value when the x value is 0 and the on current value when the x value is 1 volt. Next, by dividing them, you will get the I-on IF ratio. Next is the threshold voltage. We are using this code to find out the threshold voltage. Next is the current at when the VGS voltage is equal to threshold voltage. Next is the formula for the average subthreshold slope. Next, leave it NVT1 and NBeta1 and the N theta1 and move to the GM. GM is the transconductance. By applying this formula, you will get that file by the name GM1. The name of the file I had given gm1 underscore epcp.dat. Next, the maximum value of the transconductance you will find out by using this formula. The same formula I have also applied for when the VDS voltage is 1 volt. That is this one. Same formula. I have run this program at two different voltage. We can also find out the DI bell from this code also. By applying this formula, threshold voltage at 50 millivolt and the threshold voltage at 1 volt, divide by 1 volt minus में 50 millivolt, you will get the DIBL value, drain induced barrier loading. This is the outcome. First outcome, when the program is run at 50 millivolt. First parameter is sub-threshold slope. We are getting approximate 60 millivolt per decade. I off current is 1.4 into 10 raised to the power minus 21. I on current is 3.4 into 10 raised to the power minus 10. At VGS voltage is equal to 1 volt. By dividing them, you will get the I-on I-off ratio. Next is the threshold voltage, this one. Now the current at the threshold voltage is this one. This is the average sub-threshold slope. I have already told you about the difference between the sub-threshold slope and the average sub-threshold slope in my TFET video. Next is the same NBT1. This is the same as threshold voltage. This is the N beta 1 and gamma 1, leave it, and theta 1. This is the transconductance DAT file. When the VDS voltage is at 50 millivolt, this is the maximum value of the transconductance. Next, when my program is run at 1 volt, we are getting the different value. Sub-threshold slope is approximately same when the program is run at 50 millivolt, is again 60 millivolt per decade. Now there is a difference between the I off current and the I on current and their ratio also. This is the threshold voltage when the VDS voltage is at 1 volt. When the VDS voltage is 50 millivolt, threshold voltage is approximate 0.5 volt. But when the VDS voltage is increased to the 1 volt, the threshold voltage is reduced to 0.38 volt. This is the current at the threshold voltage. And the last one is the DIBL. By using this formula, this is the threshold voltage at 50 millivolt. This is the threshold voltage at 1 volt divided by 1 volt minus 50 millivolt. You will get the DIBL, drain induced barrier loading. When you run this program, you will get the two files. One is the structure file and one is the log file. This is the log file I got when run the program. We are getting two different curves. One is for the VDS 50 millivolt and the second is for the VDS 1 volt. This is the linear curve. By clicking on the display and click on the log, you will get the log curve. If we want to abstract this data, go to the file, export, save at the D, export in the CSV format. You will get the data in the Excel format. Okay, export succeeded. Okay, you can check that the on current, off current, threshold voltage, everything from this exported value. This is the 3D view of the structure file and this is the 2D view of the structure file. Electrostatic doping is applied at the drain side and charge plasma technique is applying at the source side to induce charge carrier. Spatial length is 10 nanometer. We are using the HFO2 material. I have run my program at three different work functions. When I am using the cobalt as the gate material, when I use ruthenium as the gate metal, when I use molybdenum as the gate metal. This is the linear curve and this is the log curve. Transfer characteristics with and without GaNs molecule for IGZO vertical nanowire field effect transistor, ammonia GaNs sensor for cobalt used as a gate electrode. When ammonia GaNs is introduced at the gate metal electrode, the work function of the gate metal electrode is changing. Their type is the change in the work function of the gate metal. When it is 0 milli electron volt, this means no ammonia GaNs is introduced at the gate metal. When there is some ammonia GaNs is introduced at the gate metal, the change in the work function is 50 milli electron volt. Next is for the 100 milli electron volt. Next is for the change in the work function of the gate metal is at 150 milli electron volt, 200 milli electron volt, and the 250 milli electron volt. This is the linear curve of the drain output characteristic, and this is the low curve. This is for the cobalt used as a gate electrode. Next figure is for when molybdenum used as a gate electrode. Same, this is the linear curve, this is the low curve. Next is the transfer characteristic curve when ruthenium is used as a gate electrode. For ammonia GaN sensor, cobalt, molybdenum, and the ruthenium metal are used as the gate electrode. These metals are very high sensitive towards ammonia gas molecule. When ammonia GaNs are exposed to these metals, then there is a slightly change in the work function of the gate metal. By changing the work function of the gate metal in the code, the electrical attributes is also changing, so that there is a change in the I off current, I on current, and the threshold voltage of the proposed device. Next is the sensitivity. A significant reduction in off-state current and on-state current can be seen as the work function is increased. Increased work function reduces the minority charge carrier to decrease the off current and confine the channel area for flow of the majority charge carrier after saturation that reduce the on current as well. Therefore, we can sense the ammonia gas molecule by the measure of change in the I off and the I on current. The sensitivity formula for the off current is this one. I off current before the GaNs absorption divided by the off current after the GaNs absorption. The formula for the on current sensitivity, I on before the GaNs absorption minus I on after the GaNs absorption divided by I off after the GaNs absorption. The sensitivity with respect to I on and I off are calculated for the proposed IGZO vertical nanowire field effect transistor based ammonia GaN sensor by the use of catalytic metal gate on the gate, cobalt, molybdenum, and the ruthenium. And its sensitivity was the change in the drain current for IGZO vertical nanowire field effect transistor with a change in the work function of 50 milli electron volt to 250 milli electron volt of the catalytic gate electrode for the ammonia GaN sensor. Their type is the change in the work function of the gate metal. When the ammonia GaNs is adsorbed over the gate metal, sensitivity can be estimated with respect to variation in I off current, I on current, and the threshold voltage. IGZO vertical nanowire field effect transistor for ammonia GaN shows higher off current sensitivity for molybdenum and the on current sensitivity for cobalt. Cobalt is the cheaper material. Cobalt as catalytic gate material is better option to make economical ammonia GaN sensor. IGZO vertical nanowire field effect transistor based ammonia GaN sensor can be used for many applications like environmental, automotive, chemical industry, and medical diagnosis, and it can also help in calculating the ammonia concentration in these fields. This is all for today. Please stay tuned